So, good morning, everybody. And I will make a presentation that is a joint work between me and Professor Rubens Sampaio. We are both from PUC-Rio. We are in the Mechanical Engineering Department. And I would like to discuss with you guys, three expressions that we find in the literature that are very common, but they are used by the authors with different meanings. So we started to doubt about the real meaning of them, and these three expressions are uncertainty quantification, uncertainty propagation, and reduction of uncertainties. So the presentation has three parts, which part to discuss which one expression, and we're going to start with uncertainty quantification. So first, I will present our definition to uncertainty, and I will discuss some strategies that we find in the literature to measure uncertainty. We can see a lot of problems with them, and we'd like to discuss and share these problems with you. And to better explain these problems, I will present three examples. So three very simple examples where the problems are very clear. And after, we'll discuss uncertainty propagation and the construction of a probabilistic model. And in the last part, reduction of uncertainties. So let's start with uncertainty quantification. So what everyone agrees? Everyone agrees that we have uncertainty when the decision is not clear. So let's suppose I have n events. So, here, x1 until xn, and each event has one probability of happen, p1 until pn. Everyone agrees that the maximum uncertainty will happen when I have all the probabilities equal. So, and when p1 is equal to p2 until pn, I have maximum uncertainty. And I have no uncertainty when one of them is 1 and all the others are 0. Okay? In our definition, uncertainty is a function, is the cumulative distribution function of our random object. So of our random variable or random vector. So here is our definition. Uncertainty is a function. But to use cumulative distribution functions to describe uncertainty is very clumsy, because how can you compare two functions? How can you say, oh, this random object is more uncertain than the other one if the uncertainty is given by a function? So it's not evident how we can make comparisons. So it would be better to have a simpler way to measure uncertainty, to describe the uncertainty. And in the literature, we found this simple way. In the literature, people use a small set of statistics to measure uncertainty. So the idea that is in the literature is, instead of use your random object with your cumulative distribution function, you make a reduction. You get just a set of statistics. And what can be these sets? For example, one set is the mean and the standard deviation. So you get the mean plus one standard deviation, the mean less one standard deviation, and you get an envelope. So you say that the uncertainty is given by this envelope. The second one, you get the coefficient of variation, which is the standard deviation divided by the mean. The third one is channel entropy. So we're going to discuss the use of these sets of statistics to measure uncertainty, okay? And the problems that we see can be divided in three classes. The first one is a dimension. We have a problem of the dimension of the statistics. We have a problem also with the meaning of them, because they have different meanings. So how statistics with different meaning can measure the same thing? So it's complicated. And also, the different measures that we find, they're not compatible, because if you order the uncertainty using one of them, you can get different order if you order the uncertainty using the another with other measure. So they're not compatible, and we're going to show this through examples, okay? So to discuss the first problem, which is the dimension, would be very useful if you could measure the uncertainty of all random objects using the same set of statistics. But this is not possible because if you have a random variable, the variance, the coefficient of variance, and entropy are scalars. But if you have a random vector, variance now is a vector, coefficient of variation is a vector, covariance is a matrix. So we have different dimensions if I change the object that we are observing. And if I have a stochastic process, it's more even complicated because the variance now is a one variable function. And the entropy, the covariance is a two-variable function. So it's even more complicated. And with the entropy, we have another problem, that is, if you have a discrete random variable, the entropy is equal or bigger than 0. But if the entropy is, if you have a continuous random variable, the entropy is a real number. So we have problems with it, okay? The meaning of the statistics that are the second problem. Different statistics have different meaning. And here I show the statistics of a continuous random variable, say the mean, the variance, the coefficient of variation, the entropy. Okay? And to discuss this meaning, we'll take a look from a geometric point of view. Okay? So I'll now formulate a problem. Suppose that I have a random variable, x, here, and I would like to approximate this random variable by a constant, by a number. Who is the best number? So I call this number the best number by lambda, and I'd like to find the lambda that will give me the best approximation. To solve this problem, we make orthogonal projection of our random variable, and we'll discover that the best number is the mean. So if I'd like to represent, to approximate our random variable by a number, the best number is the mean. And who is the error that we're going to make in this approximation? The error is the standard deviation. So the quadratic norm of our error will be the variance. So variance, standard deviation, coefficient of variation are related to errors. Okay? So different statistics have different meaning. And so how can all of them describe uncertainty with different meanings? So they're not measures of uncertainties. They are measures of errors. Okay? So to discuss the first problem, which is different measures, different statistics are not compatible, we show three examples. The first example is it. You consider a family of random variables. All of them have bimodal density function, like this one, okay? And they are parameterized by the distance between, the distance here, okay? Between it's not peaks, but the distance between the peaks. Okay, so here I show the density of this family. And for this family, I will compute the variance and entropy. When I compute the variance, I see that the variance is a function of the distance between the peaks, the distance, okay? And the entropy for all of them does not depend on d, is equal to 0. So if I increase d, I increase the distance, variance changes, grows, and entropy remains constant. Entropy doesn't change. So I can vary variance with fixed entropy. So I have a problem with it. They are not compatible. In our second example, now we're going to consider a family of Gaussian random variables. Okay? And they are parameterized by the mean, mu. Okay, and for this family, I compute the entropy. When I compute the entropy, I say that the entropy depends on the variance, sigma square, but doesn't depend on the mean. So this states to me that I can make a translation of the gamma density, so I change the mean, and I keep the variance. I change variance, I change the coefficient of variation, but I don't change the entropy. So entropy and coefficient of variation are not compatible. And our third example, we're going to take a look at the gamma density function. So I get a random variable with gamma density function. Okay, I compute mean, variance, and entropy for this random variable. And now I'm going to make a graph of entropy against variance for different means. So here, for each line is a different mean. Okay, so let's take a look at the mean one, the red curve. So here I see that the variance grows and entropy decreases. So entropy and variance may vary in different sense. So they are not compatible. One is growing and the other is getting every time lower. So they are not compatible. Okay, here if I take a look at the green curve, is even more interesting because for variance lower than 9, I see that the variance is growing with the entropy. But for variance bigger than 9, it's decreasing. So depending on the interval of variance that I take a look, I have a different behavior. Okay? Now, I discussed the first problem, which is uncertainty quantification. Now I'm going to discuss the second problem, that is uncertainty propagation. What we think about uncertainty propagation? I have an input, which is a random object. It has uncertainty. And this random object will suffer a transformation. Okay? And in the output, I have another random object with uncertainty. Well, to understand this problem, we'll take a look in this very simple system, which is composed by a spring and a mass. So the spring has a stiffness key. The position of the mass is x. The equation of this motion is very simple, and the solution is this one. The solution, the position of the particle over time, is this one, okay? Very simple. And now I will consider that the stiffness of the spring key is a discrete random variable. So it has Bernoulli mass function, so it assumes just two values, 1 and p squared divided by 4, with equal probability, and the transformation that I make is this one. Okay, this is a transformation. And now the response is a stochastic process that I call x here. And for each instance of time, I have a random variable with Bernoulli mass function. A discrete random variable with Bernoulli mass function. And I will compute for the input and the output the statistics. Variance, coefficient of variation, entropy, and the output mean, variance, and entropy. And I see that the entropy in the input is 0.69, and in the output is constant over time, is 0.69. So the entropy will not change. But the mean and variance are functions of time. So if I take a look at the envelope graph of the response and the entropy graph, they're completely different. So here in dark blue, we have the mean, and in light blue, we have mean plus a standard deviation and mean less standard deviation. The two graphs are completely different. So here it seems that the uncertainty is varying over time, but here it seems that this is constant. This example is even more interesting if I add a deterministic force that is acting over the mass. So now I have a force here over the mass. The force is growing with time, t, and now the solution of my problem, the position of the mass, is this new function. Okay, so I have a new term here. And now I make the same thing. I suppose that the stiffness of the spring is a random variable, discrete random variable with Bernoulli mass function, is equal than we did previously. And the output now is a stochastic process. Okay, I compute the input and the output, the statistics, and I plot the envelope graph of the response and the entropy graph. Here, the entropy remains constant. It doesn't change. Constant line. But here, it seems that the envelope is getting larger. Is it correct? I can measure the uncertainty with using the envelope. What is happening with the uncertainty over time? Is growing? So to answer this question, we plotted the graph of the variance over time and the graph of the coefficient of variation over time. And here I see that no, the variance is varying over time. It's not always growing, sometimes getting lower. And the coefficient of variation has a peak here between 0 and 5. So the envelope here is lying. It's not telling us the right information. It seems that it's getting larger, but actually, no. The variance grows and after decreases. Okay? So all of these measures are not compatible. I cannot compare them. I cannot use in the same problem the two of them or three of them. Okay? But how can we measure uncertainty propagation? That is a good question. It's very useful if you know a way to measure it. And what is usually done in the literature? Okay, you measure your uncertainty in the input with entropy. You measure the uncertainty in the output with entropy. And you're going to try to find the relation between them. But this has a problem. So let's see the problem. So suppose that my transformation will get the modulus of a random variable. So I have a random variable x, and I'll get the modulus of it. Okay, and I assume two possible distributions for the input, for x. In my first model, I assume that it's uniform over -1 and 1. And in the second model, I assume that it's uniform over 0 and 2. In both cases, I have the same entropy, 0.69. Okay? And in the output for the first model, the entropy is 0. And for the second model, the entropy is 0.69. So I have in the input the same entropy of the two models and the output different entropies, which says that there is no function relation between the entropies. I cannot find the function relation. It doesn't exist in this case. Okay, so this strategy is complicated. I have a problem. And the second point that I'd like to discuss here in uncertainty propagation is the construction of a probabilistic model. So I would like to construct a probabilistic model for my input. If I have a lot of realizations of my input, I can make an histogram and I will approximate my distribution from this histogram. But this is complicated if I have a high-dimensional object, random objects, for example, random vector in high dimension. But okay, it's a way. But if I have few or non-realizations of my random object, I cannot compute an histogram, a good histogram, okay? So what does the literature say to do? Use the maximum entropy principle. So that's what we're going to do. So in the input, I have a random object, and I choose for it a probabilistic model with maximum entropy, so I respect the constraints of my problem. And in the output, I have a random object. So why I should use the maximum entropy principle? Because the distribution that I'm going to find with the principle to the input may be very different from the really one, from the true model. So this is a problem. And the second problem is that if I use the maximal entropy principle to construct the probabilistic model of the input, I don't assure that in the output I will have maximal entropy. It's not sure that in the output I'll have maximal entropy. So to understand this, to show this, I want to present a very simple example. So I consider that I have in the input a random variable x, and this random variable we're going to make a transformation with this random variable, and you get a new random variable I. Okay, so here is the transformation. And for the input, we assume two possible models. In the first model, I assume that it's uniform over 0 and 2. And in the second model, I assume that it's non-uniform into 0, 2. Okay? So here in the input, I have my two models, uniform and non-uniform. The uniform has maximal entropy. And in the output with I, the maximal entropy comes from the second model. So I have maximal entropy in the input, but I don't have but I don't have maximal entropy in the output. So wouldn't it be better to have maximal entropy in the output, not in the input? So this is another question. And now I'd like to talk briefly about reduction of uncertainties. So it's an expression very common in the literature. We find several papers using it, but it's not clear what people really means about reduction of uncertainties, because if you have a fixed distribution in the input and you have a fixed transformation, the output is fixed. You will not change the output. It's given, it's fixed. So if you'd like to change the distribution of the output, you have to change the input or you have to change the transformation. So with fixed input and fixed transformation, no reduction is not possible. You cannot say no, we cannot talk about reduction. But even so, we'd like to talk about reduction of uncertainties. The first thing that would be required is to have a measure of uncertainty. So we have to have a measure of uncertainty to enable comparisons. So I can say, oh, this one is more uncertain than the other. So I have to answer my first question is, what is uncertainty quantification? And the second point is that to modify the probabilistic model of the output, I have to change the probabilistic model of the input, and I have to solve an inverse problem. Say, who is the probabilistic model of the input who will give me lower uncertainty in the output? So it's like an inverse problem. So it's really complicated, and we don't know how to solve this. So the final remarks is that the measures that we find in the literature the measures that the literature says that can measure uncertainty, you're not sure about them. They don't seem to be a good reduction. So doesn't seem to be a good idea to change the cumulative distribution function for these sets. So variance, coefficient of variance, and entropy doesn't seem to be a good reduction. And we don't know yet who is the set, or if exists a set that will make this reduction in a nice way. We don't know who is this set, so it's an open question, and we think that it's better to use the cumulative distribution function until we don't know this set. So it's better to use the cumulative distribution function. But we have a lot of questions, and I hope you can help us to understand and to find the answer to them. So thank you for the attention.